Okay, we can continue, ladies and gentlemen. So I was saying, if you understand from the onset that the degree of the polynomial you're looking at is n, and then in that case, you can even omit that notation for n, okay? So I was trying to look at this property in the previous meeting. We are saying L nk xi is equal to 1 if I is equal to k and is equal to 0 if I is not equal to k. Okay. So in our case, we are looking at the linear interpolating polynomial. So I can even write the L0 as L10. So the first one there is just the degree of the polynomial. Okay, so we found L10x to be equal to x, minus 1 over 3. So we found this to be equal to minus 1 over 3. And then we have x minus 5. And we found L11x to be equal to 1 over 3, x minus 2. Okay, so let us verify if that property is satisfied in this case. So we need to find L10 x0. So in this case, I can see that these values are equal, the I and the k. So in this case, 0, 0 there. Okay, so if I look at that, it is going to give me what value? So L10 x0 is just equal to 2. So I have 2 there. If I substitute in there, I'm going to get 1 over 3 times 2 minus 5. And you will see that this will just give you 1. Okay. Try to get now L10 at x1. So in this case, so like in the first case, let me write this thing here. So in this case, the first expression, we have I equal to k, because 0 is equal to 0. But in this case, I is not equal to k, because 0 is not equal to 1. So according to that property, I expect this to be equal to 0. So let me try to evaluate this. So L10 at x1 is just equal to 5, right? And this will just be equal to 1 over 3. Negative 1 over 3, then 5 minus 5. And definitely, this is just equal to 0, right? So you can also verify using L11. You should be able to see that this property is satisfied. Okay, so now let us go back to LNKX. So I need to construct LNKX, and then after constructing this, I'll be able to find the interpolating polynomial. Now, you notice that in that previous example, when evaluating this at 0, at k equal to 0, we are not including in the numerator, we are finding the product of those linear factors, so to speak. Okay, so for example, looking at the example we had, we got that linear factor x minus x1. We excluded the other factor x minus x naught. We won't include this in the numerator. Okay, so we'll do this, and then in the denominator, we are going to evaluate this same x minus x1 at the point x0. So that's why we're getting x0 minus x1, right? So in order for us to construct LNKX, we need to have in the numerator, so maybe now let me delete this. So, or maybe let me keep it like this, and then I just talk about the numerator. So in the numerator, we are going to have the product of those linear factors. So we're going to have x minus x0, for example, x minus x1, and so on. But we won't evaluate the one at xk, x is equal to xk. So we are going to have x minus xk minus 1 up to there. And then the next value, I've run out of space here, so maybe let me continue on top there. So the next value will be x minus xk plus 1. So we'll skip the one which will have x minus xk. Okay, and then we'll continue up to the last one, which will be x minus xn. And then in the denominator, we need to evaluate now that expression we have in the numerator at the point x equal to xk. So in the denominator, I should have xk minus x naught. Then the next one will be xk minus x1, and so on, up to the last one, which will be xk minus xn. Right? So that's what I'm going to do. And that should be able to help me get the nth Lagrange interpolating polynomial. So using this lnkx, you can, for example, list all the expressions you are going to get when n is equal to 2, right? So when n is equal to 2, let me move to the next board. When n is equal to 2, that is when I'm looking at the interpolating polynomial of degree 2, then I expect, of course, to have 3 points. We talked about this already. So I will have x naught, comma, y naught. The next value will be x1, comma, y1. And lastly, I expect to have x2, comma, y2. Okay? And then in this case, L20, of course, you always start from 0. L20x will be equal to what? I won't have a linear factor with x minus x0, right? As we stated there. So I'm going to have x minus x1, this factor, then times x minus x2. I'm going to get only this in the numerator. I won't have x minus x0. No, this won't be included. Then I'll say this guy divided by evaluating that numerator at xk. So xk in this case is x0, right? Because k there is 0. So I'm going to say x0 minus x1 times x0 minus x2. So that's what I'm going to get. If I move on to L21x, so in this case, k is equal to 1, then I'm going to evaluate, I'm going to get the numerator in this way, x minus x0. I won't have x minus x1. The next and the last value will be x minus x2 here. Then in the denominator, I'm going to have the value of this numerator at the point x is equal to xk. So I'm going to have x1 minus x0 times x1 minus x2. And lastly, L22x equal to what? X minus x0, x minus x1. I won't have x minus x2 here. And then I'll divide this by x2 minus x0 times x2 minus x1. That's what we're going to get. From here, I can even construct L3kx when n is equal to 3. That means when I have 4 points there, I can even do that. Okay, is that okay, ladies and gentlemen, so far? Any questions on this part before I give the nth Lagrange interpolating polynomial? Okay, So now, let's give the nth Lagrange interpolating polynomial. And if you check in your notes, this one is appearing as theorem 4.1.2. Okay. So in this case, of course, I expect to have n plus 1 distinct points. Okay. And these will be x0, x1, and so on up to xn. And I'll get corresponding values of f from those. Then I'll be able to make sure that this polynomial p is interpolating the given data. That is, f of xk should be equal to p over xk. So at those given points, I need this equality to hold. And then in that case, I will have px, which will be given as follows: f of x0 times ln0x. You can find the value of n0, n0 ln0x. Then you substitute it there. Then the next value will be f of x1 times ln1x. And then you continue in the same manner up to the last point, or the last expression, which will be equal to f of xn, then ln x. Okay, where this lnk will now be given by what? Of course, if you want, you can write this using the sigma symbol. You can write that as a summation of fxk lnk from k equal to 0 to n, right? So lnk in this case will be given by x minus x0, then x minus x1, and so on times x minus xn minus, xnk minus 1. Then I'll skip x minus xk. So I'll move on to x minus xk plus 1. And then I'll continue like this up to the last expression, x minus xn, everything divided by the value of this numerator at x equal to xk. So I'm going to have xk minus x0, xk minus x1, and so on up to the last one, xk minus xn. That's what I'm going to get. Okay. Now these points have a special name. Okay, these points x0, x1 up to x0, they are called nodes. Okay, so that's what we'll get. And this p is the one we are calling the nth Lagrange interpolating polynomial. Okay, is that okay, ladies and gentlemen? Any questions on this part? So all you need to know is how to construct lnk, and then you'll be able to substitute in p. You already have f of x0, f of x1, and so on up to f of xn. Okay, can we look at an example now? People are not responding. Okay, let me move on to the next board then.
We can
and
move
then
on.
we look at an example. Okay, thank you. I feel like I'm just alone in this meeting. Are we together, ladies and gentlemen?
Yeah, following.
Together.
Yes, sir.
Okay. Okay, then thank you. So remember that I gave you this formula, this function, f of x is equal to 1 over x. And I said you can use the Taylor theorem to approximate f of 3. So the Taylor polynomial will be expanded about the point x is equal to 1, right? You remember that example? And we said this one will give you inaccurate values. Now let's try to use Lagrange interpolating polynomial. And then we just consider 3 points. Okay, so we just consider 3 points. So I'll wrap this part and say in this case, we'll consider this at x0 equal to 2, x1 equal to 2.75, and x2 equal to 4. Okay, So for those values of x, I can find f of x naught. So f of x naught in this case will just be equal to 1 over 2. F of x1, okay, this will just be equal to 1 over 2.75, okay, which will be the same as what? This will be the same as 4 over 11, right? And lastly, f over x2 will be equal to 1 over 4. So I'm just substituting them in the function f. I need those in order for me to find the Lagrange interpolating polynomial. So the question here says find the second Lagrange interpolating polynomial. Okay, so that's what we want to look at. So all I need to do is to find expressions for L and Kx, right? So I'll start with L20, right? So the 2 there again is just representing the degree of this polynomial. So this one will be equal to, like we said, we'll have those linear factors in the numerator x minus x1. I won't have x minus x0 because in this case k is equal to 0. So I'll have this times x minus x2. Now I'll evaluate this same numerator at x0. So I'll have x naught minus x1 times x naught minus x2. So let's just substitute in there. So we have x minus x1 is 2.75 times x minus x2 is just equal to 4, then divided by x0 is just equal to 2. So we'll have 2 minus 2.75 and then 2 minus 4. So we can evaluate the numerator there, and I guess it will be able to give you 2 over 3. So please verify that value. So you say 2 minus 2.75, it will be 0.75. 0.75 times negative 0.75 times negative 2, because 2 minus 4 will just be negative 2. So this will just give us 2 over 3 times x minus 2.75, then times x minus 4. Okay, so if you want, we can even simplify this. You expand it, you will see that it will give you a polynomial of degree 2. So we'll keep this value and move on to finding L21. So L21x will be equal to what? In the numerator, we're going to have x minus x naught now, because k is equal to 1. And then I'm going to have x minus x2 here, right? And then I will evaluate this numerator at x1. So it will be x1 minus x naught, then times x1 minus x2. So we can substitute values now. So we have x minus x naught is 2. Then x2 is just equal to 4. Then I'll divide this by x1 is 2.75. So I have 2.75 minus 2 times 2.75 minus 4. Right? We can simplify that. And then you should be able to verify that this will just give you minus 16 over 15 x minus 2 times x minus 4. So if you want again here, you can expand. You're able to see that this will just give you a polynomial of degree 2. Okay, so from this it tells us that even at the far end we should have a second Lagrange interpolating polynomial. Okay, we move on and find the last expression, the L22x. So this one should be given by x minus x naught times x minus x1. I won't have x minus x2 here. And then I'll evaluate this same numerator at the point x2. So I'll have x2 minus x naught times x2 minus x1. I substitute the values in there. So I'm going to have x minus 2 times x minus 2.75. Okay. This divided by the same expression evaluated at x2, so it will be 4 minus 2 times 4 minus 2.75. So you can simplify the numerator there. You'll be able to see, or you should be able to verify that this will just give you 2 over 5 times x minus 2 times x minus 2.75, right? So we have all the values that we need. We just need to substitute these in the nth Lagrange interpolating polynomial. So let me do it on the next board.